Fine, guys, let's start. Okay. So till now, we have seen the basics of the distributions. Fine. So I think for the last 2, 3 classes, so we have discussed about the probability distributions, and then we have seen excuse me a second, and we have seen different examples of fundamentals, right? Fundamentals of PDF and PMF examples. Okay. Now, as I have shown you this diagram, in each type of probability distribution, whether it is discrete or continuous, there are some famous distributions. Okay. These are not the only distributions, fine, but these are the famous distributions. Okay. In the continuous also, there are some famous continuous distributions or PDF functions, or here it will be PMF functions. Okay. Now, why only these? Okay. And like, even though it is the same discrete variable, why do you have different type of distributions will be the first question. Okay. Even though it is the same continuous variable, okay, why we do have different distributions for the same continuous variable? Okay. The answer is simple. So okay, I think I have already told this before, but let me tell it again. See, even though it is the same continuous variable, okay, but the type of continuous variable might be different in each case. Okay, what do I mean by that? In a normal distribution, the nature of the continuous variable could be, okay, start from minimum value, then go to reach a peak value, and then again decrease, and then settle at a minimum value. Okay, this is a continuous variable. Okay, but the nature is this way. Fine. And let's say you are having a particular continuous variable whose value is always increasing exponentially. Okay. Now here, if you see, both of these are continuous variable. Okay. That means these are not they are not like discrete. Okay. These are all, any value is possible between a given range. Okay. Both are continuous variable. Okay. That means what? Both comes under this category. That means both can be represented using some PDF functions. Agree? But the nature of this continuous variable is different from this continuous variable. In exponential, you cannot see again any downfall. Okay. It's always increasing. Okay, so that's why different distributions will be required to study different type of continuous variable. Okay, for this we will be going for new normal distribution based upon its shape and the behavior, and for this we will be going for the exponential distribution. Okay, that's why there are different types of distributions inside the same continuous variable. Similarly, in the discrete also, there will be different types of natures different for each discrete variable. Okay, for Bernoulli it will be some conditions for the discrete, and for binomial it will be different, uniform will be different. Okay, when we study this I'll be letting you know. Okay, but just understand that even though we are calling it as a single word discrete, but there could be different types of discrete, just like how you are having different type. This is different type of continuous, this is also another type of continuous. Okay, but we are calling just by the umbrella word called as continuous. Inside that umbrella level, you have different types of distributions. Okay, that's the first point. Now, second point is like different types of distributions, right? So we will be seeing, okay, these distributions. Okay, and as I said, these are not the only discrete distributions available out there. Okay, and these are not the only continuous distributions. Okay, but these are the famous. Because why they are famous? When something will become famous, when it is mostly followed or mostly available in the nature. Okay, in the actual day-to-day life, you can find these distributions very often. Okay, but there might be so many lots of distributions. Okay, but we are not going to study all those. Okay, because these are the very famous which you can observe in day-to-day life. For example, in normal distribution, right? So you can see lots and lots of distributions in the day-to-day life. Lots and lots of events will follow normal distributions. Okay, we'll show you that. Okay, that's the reason we have some famous few distributions in each category. Fine. So now let's go and see some practical code, because we have done with the theory. Okay, so much theory will again okay will again not be that helpful. Okay, now let's see some code. See, probability distributions. Okay, see, many statistical tools and techniques used in data analysis use based on probability. Okay, probability measures how likely it is for an event to occur on a scale from 0 to 1. Fine. 0, it doesn't occur. Okay, oh sorry. And 1, it will occur. Now, when working with data, okay, when working with data, variables in the columns of test data can be thought as a random variable. Fine. And random variables that vary due to chance. A probability distribution describes how random variable is distributed. It tells us the value a random variable is most likely to take and which value you're going to take. Same thing with the probability distribution, which we have studied in the first class of this concept. It's also saying the same thing. What's the probability that a random variable will be took? Okay. There are okay, fine. So now I'm saying the first distribution which we are going to see will be the uniform distribution. Okay. The word uniform will also tell you that okay the distribution is same or uniform. Okay, see, the uniform distribution is a probability distribution where each value within a range, certain range, is equally likely to occur and value outside the range never occur. Okay, we might make a density plot of uniform distribution. It appears flat because no value is any more likely or dense than the other. Okay, fine. So we are going to use a SciPy. Fine, we are going to use a SciPy.stats library. As you know, we have famous libraries, power packages, NumPy, pandas, fine, and we have matplotlib, and SciPy. Okay, so NumPy for the arrays, numerical Python for the array matrices operations, pandas for data frames, matplotlib, okay, for visualization, SciPy for statistics mostly. Okay, and apart from this, finally you have something called as sklearn, which is the master library for the complete machine learning. Okay, fine. Now today we are going to focus over here, the SciPy part. Fine. So now in SciPy, we already have so many predefined functions for the stats. Fine. See, the first thing is you need to import. So yeah, so as you can see, all the four things which I've just mentioned are imported. Okay. And uniform data stats. See, in SciPy.stats as stats. Okay. Inside the stats, you have stats dot uniform dot rvs. Okay, and you are giving this. Okay, now what is this function? Okay, so here I have returned an over here. Yeah, so if you see stats dot distribution dot rvs, okay, this generates random numbers from the specified distribution. Okay, so whenever you want to generate a random numbers or the random shape from a specific distribution, so you need to use stats dot distribution dot rvs. Okay, now whatever distribution you want to give, sorry, whatever distribution you want to give in the distribution place and rvs. So that's why I'm giving, I want to generate a uniform distribution. Okay, so that's why stats dot uniform dot rvs. Okay, and the parameters will change accordingly. Okay, the argument to rvs will vary depending on the type of distribution you are working with. Okay, for a normal distribution you will pass something, and for uniform you will pass a different parameters. Okay, in case of uniform distribution you have to specify the starting and ending points and the size. Okay, so that is with this function. Okay, so now I'm using stats dot uniform dot rvs because I want to create a uniform function. And here, as I said, the arguments you need to pass are starting, ending, and the size. Okay, so I want to start. LOC is a start and scale is a end. Okay, and the size is a size. Okay, so I want to generate how many 1 lakh. So 1 lakh data points I want to generate, and it will start from 0, it will end at 10. Okay, but all this should form a uniform distribution. Fine, and that is created, uniform data is created, and you can just plot this uniform data. Okay, using this period data frame. You're creating a data frame out of this, and you are plotting, and density plot you are plotting. Okay, kind equal to density. Okay, these are just figure is the shape size of the your diagram, and xlim is the just the shape of the, I mean the size of the starting and ending. Okay, because if you can start from the minus 0, if this is 0, right, so here it will be -1, and 0 10 will be 11. Okay, so from -1 to 11 you are just creating the diagram, but inside this 0 to 10 only, 0 to 10 only, our diagram will, our what do you say, normal distribution will be falling. Fine, so this is how you, the main thing is you just need to know how to draw a uniform distribution. Okay, stats.uniform.rvs, size, starting, ending. Okay, now if you see, when we plotted, we got this diagram. Okay, so in this diagram you can clearly see this uniform distribution. Okay, the starting, the first value 0 and final value 10, but if you see the frequency is almost same. Agree, the frequency is almost same. It's not like this, it's not like this. So normally in any histogram, if you see, okay, in histograms, if you see, if you remember, yeah, so here, yeah, so if you see See, these are the values and this is a frequency. Fine. So for 35 to some 38, the frequency is very little. Okay. And frequency is increasing, as you can see. Agree? And frequency is again decreasing. So that's why the graph is became like this. Okay, if you see here using Seaborn, yesterday we have seen the graph is like this. Okay, the frequencies are different. So here also, if you see the frequency when you are rolling 2 days and some, so the clearly you can see the probability of the frequencies are constantly increasing and decreasing, which is creating a normal curve. Fine, but here in the uniform distribution, there will not be any such scenario. Okay, each and every value. So that's why it is saying if you are given a range from 0 to 10, the probability for each and every value between this will be same. Okay, and anything outside this will be 0. Fine. So that's why each and every value is at the same height, same y level. Okay, the probability is almost 0.1 only. Okay, so this type of distribution is called as uniform distribution. Okay, so in the above code we have generated 10,000 points from a uniform distribution spanning between 0 to 10. Okay, we see the density of uniform data is essential level, meaning any given value has the same probability of occurring. Okay, there are no different probabilities for different values. Okay, it's the same probability. Okay, the area under the probability density curve is always equal to 1. Okay, the overall area will be obviously equal to 1. Fine. So now the stats.distribution.cdf. Okay, you remember CDF, the cumulative distribution, is used to determine the probability that observation drawn from the distribution falls below a specific value. Okay, the same thing we have seen. So fall below a specific value. Okay, that means what? If you're asking for 4, it will tell you what is the probability. Okay, what is the probability that we are going to find a value x is less than or equal to 4. Fine, x is less than or equal to 4. Fine. So now in essence CDS gives you the in essence CDS will give you what? It gives you the area under the distribution density curve to the left of a certain value on the x-axis. Fine, it will give you the area. Same thing which we have seen the other day. Okay, so in the CDF, how you are getting 0.8, will consider if it is 1. Okay, 0.8 means if it is 1. Okay, it will consider all the area till this point. Fine, the same thing is happening over here. So it will consider the area to the left of the certain value of the x-axis. Okay, so in the above example, if there is 25% chance that observation will be in the range of 0 to 25. Okay, 0 to 2.5. Okay, so here, okay, if you have 2.5, okay, then it will add each and every value probability for till 2.5. Okay, so then what we are going to get? See, and 75% chance it will fall in the range of minus 2.5 to 10. Okay, that means what? It will give the complete area. So 0 to 10. So here we will have 5. Fine, and let's say over here. Okay, fine. So CDF, the maximum value is what? CDF maximum value is 1 because this is a area. Okay, I've mentioned this multiple times. The maximum value of CDF is 1 because the overall CDF will give you what? Probability, overall probability. The maximum value of if you take the maximum value, so that should cover the all values. So how much probability you are covering? 100% probability. That means probability will be 1. The maximum value of CDF will be 1. Fine. So now that's why if you ask what is the probability that x will be to find a value that will be less than or equal to 10. Fine, that means you are covering till this point, so it will consider the overall area and that will be equal to 1. Fine, but now if you ask what is the probability for 5, okay, x is less than or equal to 5. Fine, so that it will be over here, the middle part. Okay, it will consider the half area, so that will be equal to 0.5. Fine. Similarly, if you ask for 2.5, it will consider only this much area, and that will be probability of 0.25. Okay, or 25%. Getting? So that is the CDF you are getting. So that's why it is saying to find in the range of 0 to 2.5, you will have 25% chance to find observation. Okay, in the range of 2.5 to 10, you will have 75%. Okay, in the range of only 2.5. Okay, usually if I ask x equal to 7.5, what it will do? It will do x is less than or equal to 7.5. That means what? Here if you have 7 and 7.5, okay, usually it will take from here to all, from 0 to 7.5, it will consider, it will tell you 7.5. Okay, fine. So now Similarly, it is saying what? Yeah, from 0 to 2.5 and 75% chance from 2.5 to 10. Okay, from 2.5 to 10. Fine. So usually if I say x, if I want to find out 10, the cumulative, what it will do, it will say x is less than or equal to 10. That means what? From 0 to 10, it will consider all the value. But if I only want 2.5 to 10, fine. That means what? You need to integrate the function from 2.5 to 10 only. Okay. So then what it will do, from 2.5 to 10, you can consider. Okay. That will give you 75%. Fine. So now I have a question here, guys. I have a question. So can someone tell me, see, if I ask a value, if I ask a value for the cumulative, if I ask for 4, it will give you x is equal less than or equal to 4. If I ask for 6, it is going to make x is equal less than or equal to 6. Fine. Because that means what? The minimum value it is always taken by default. Agree? So now how to get only between 2 to 10? Did you understand my question? If I ask for 2, it will give x is less than or equal to 2. Agree? If I ask for 10, it will give x less than or equal to 10. Fine. If I ask for 2, it will give you this area. If I ask for 10, it will give you whole area. Okay. But my point is, how can I get only between x is less than or equal to 10, but again greater than or equal to 2? Okay. I want only between this area. Can someone just think of? Sorry.
We can subtract the remaining part from total part.
Superb. So you are saying, yeah. So you are saying, first take x less than or equal to 2, you will get this part, and then x take less than or equal to 10, you will take this part and just subtract this one from this side, so that you will get this part. Is that what you are saying?
Yes.
Yes, perfect. That's expected. That's how you can get for individual values. Okay, for individual values. Fine. So that's how you can use. So usually cumulative will directly give for 8. 8 means it will give less than or equal to 8. But if you want to find out only 6 to 8 or 4 to 8, as you said, you can subtract those values. Okay, super. Now that's regarding the uniform function, guys. So it's not.
Your voice is breaking up, Santosh.
My voice is breaking. Okay. Connected from mobile data. Just let me check my internet, guys. Sorry, just give me a second. Is it better now? Hello? Hello?
Yes, sir. Better.
It's better? Okay, fine. Sorry, guys, some issue with my Wi-Fi. Okay, fine. So now, okay. Now, if you see, so that's regarding the uniform. So I would say you'll not use uniform that much, okay, but it's better to know some functions about that. Okay, so same thing, stats.uniform CDF. Also you have stats.uniform dot CDF. Okay, it will give you if you ask like 2.5, okay, from 0 to 10, you want to find out 2.5, that means what is the probability to find a value that is less than or equal to 2.5? The probability is 25, 0.25. Okay, so same thing you can get off. And similarly, you have something called as PPF, okay, which is the reverse of CDF. Okay, that means what? CDF will tell you the probability, okay, for a given value. PPF will tell you the value at a given probability. Okay, that means if you want to know the cutoff value for which 40% of the chance, okay, you're only saying 40%, that means 0.4 of probability can be found below which point. Okay, for that you need to use the PPF. Okay, for that you need to use the PPF. And just as you can see, PPF, probability point function, is an inverse of CDF. Okay, that means PPF returns the exact point where the probability everything to the left is equal to Y. Fine. So similarly, if you have probability, you want the value, go for CDF. You have the value, but if you want the probability, you want to go for the PPF. Did I say it reverse? Yeah, sorry. So if you have the value and if you want the probability, go for the CDF. But if you have the probability, you want the cutoff value, you go for the PPF. Fine. Yeah, guys, and yeah, and if you want the PDF, okay, what the actual where all it has started from the PDF, right? Probability density function, it is where it started. And what is a probability for each and every value, guys? What is the probability for each and every value throughout this range? Can someone tell me? Uniform distribution, we are seeing the values. What is the probability or what is the frequency of each and every value over this range?
One, sir.
1? No, not the whole 0.1, guys. You know, yeah, I guess understanding. For 0, what is the probability? This is the probability, guys. The y-axis, see, in the probability distribution, the y-axis will be either frequency or probability or density, all means the same thing, right? Fundamentally, what we're doing for each and every value, what is the probability we are checking, right? So that is its distribution. Agree? So for the overall probability will be 1. Okay, but for each and every value, what is the probability? The y-axis, wherever you are seeing, right? So that is a 0.1 for every value, that is a 0.1. That is the reason it's called uniform. Means it's not like for 0, it's not like it is 0.1. For 2, it's not like 2.4. Are you guys getting? See over here what's happening for 0. For 2, what is the probability, guys? For 2, it is some 0.3. For 3, it is some 0.6. Fine. For each and every value, the y-axis, always remember in the probability distribution, y-axis will be the probability. Okay. So for each and every value, the probabilities are increasing or decreasing, always fluctuating. Fine. But that's not the case with uniform. Here, the probabilities are always almost same. Fine. For every value you take in between this range, it will always be same. And anything above 10, the probability is 0 because there is no y value for that. And anything less than 0, there is no value. Fine. That's why it's called uniform. The fundamental reason is for any value you take from the given range, it will have the same probability, almost the same probability. Getting? So now what is the probability for each and every value? It is 0.1. Okay. So that, and what is this? This is a PDF. This is a PDF graph. Fine. The one which we have seen, kernel density, what are all those are the PDF graphs. What is the PDF will you? It will give you, these are all the random variable. Fine, we don't know what is this experiment. Just going back to the basics, we are doing a random experiment. That random experiment will have some random variable, okay, called as X. Okay, this can have different values, and each of these will have certain probabilities. Fine, and this complete is called probability distribution. Basics. So we don't know what is the random experiment, but in this random experiment is having these values 0 to 10. Okay, so X is equal to 0 to for all the values between 0 to 10. And now this random variables, all these values are having some probabilities. What are those? These are the probabilities. Okay, these are the probabilities. But here the difference is every value will have the same probability. Okay, that's why it's called uniform distribution. Fine, and this distribution is called probability distribution, and specifically this is a continuous variable. It's called PDF, probability density function. Just going to the basics, guys. Don't remember. Sorry, don't forget. Okay, so now stats.uniform.pdf. Okay, stats.uniform.pdf means uniform PDF function. If you want to see density at the value -1, that means our range is from only 0 to 10. If you take any value less than 0, it will be density at -1. Sorry, -1 will be 0. Okay, and density at 2 will be 0.1. Any value between 0 to 10 will be 0.1. Okay, if you take any value greater than 10, because our range is ending at 0 to 10, because that's how we are created. Okay, starting value is 0, ending value is 10. Okay, that's how we have created. Fine. So anything above or below this will have no probabilities at all. So that's why it is -1 also, it is 0 density. And you can take density as a frequency or the probability, guys. You can take it as probability. Okay, we are saying it density. And any value greater than 10, that is 11 also, it is 0. Fine. And in between this, it is always equal to 0.1. Fine. So PDF will give you the probability, which is always same for all the values. That's why it is 0.1, 0.1, 0.1. Okay. But CDF will give you the cumulative probability. So that's why it will add. Okay. For one, it is, see, for one in PDF, for one, it will be 0.1. For two also 0.1. Okay. But that is PDF. But now coming to CDF, if you ask for 2, it will consider less than or equal to 2. That means it will consider for 2 and also 1. Okay, that means 0.1 plus 0.1. It will be 0.2. Okay, CDF will keep on adding. Okay, same scenario which you studied. So that's how you can calculate the PDF, which will give you the specific point probability, which is 0.1 always in case of uniform. And CDF will give you the cumulative distribution values. Okay, and just PPF is inverse of CDF. Fine. That's about the uniform distribution, guys. Is this clear, guys? Any doubts about the uniform distribution? Let me know. Be honest. That's completely fine.
No, Santosh.
Okay.
Some-
Others? Okay. Fine. Cool. So now the next thing we have to study is random seed. I will be letting you know when we use this random seed, there is the important thing called as random seed. Okay. After that, yeah, normal distribution, guys. Okay. So let me go back to this. Fine. So as I said, out of all the distributions, one of the most important distribution in statistics will be the normal distribution. Okay. And now we are going to study this. Fine. So now, first of all, I think by now you have the clarity that normal distribution is a continuous variable distribution, continuous distribution. Okay. And we are going to use PDF. Okay. So now normal distribution is a type of PDF. Agree? So now focus here, guys, because if you understand normal distribution, only then you will understand lots of things. Okay. For example, if you understand normal distribution, you need to understand something called as empirical formula, which is the basics of normal distribution. And based upon that, you are going to study extremely important distribution called a standard normal distribution. Okay. Most of the statistics which you do, okay, which we normally follow, will be based on the standard normal distribution. Okay. On this, again, there are some important points. Okay. So this is the fundamental basis. The normal distribution is a fundamental basis for all the concepts, mostly which you are going to study in the future classes. Okay. But it's very interesting and simple. Okay. Yet it's very important. Okay. So now see, normal distribution is also known as Gaussian distribution. Okay. Is a continuous probability distribution. Okay. That is symmetric about the mean, showing that the data near the mean are more frequent in occurrence than the data from the far. Okay. So I'll go step by step. Okay. Make sure you understand it very clearly. See, normal distribution is something which looks like this. Okay. This is also called normal distribution or bell curve. Okay. Sometimes they also call bell curve. It looks like bell, right? And also famously, it's called Gaussian distribution. Okay. It's also called Gaussian distribution. Okay. Now this is, as we have understood, it's a continuous variable distribution, and you can call it as continuous probability density function distribution. Okay. Now here, as you can see, that means what? It's this normal distribution which we are seeing over here is ranging from -0.6, okay, to 0.6. Okay, -0.6 to 0.6, it is ranging. Fine. And you have the mean over here. 0 is the mean. Fine. Average value. And normal distribution, always remember, it will be symmetric about the mean. Okay. There are some fundamental differences. It will be symmetric about the mean. That means what? 50% of the values will be this side and 50% of the values will be this side. Okay, showing that, and at the mean you will have the maximum frequency. Okay, that means at the average value the frequency will be high. Okay, so now if you consider yeah, I'll show you a few examples. Just wait. Okay, so now this is a distribution. The main thing is symmetric about the mean. Okay, and it's a bell curve. Fine. Now coming to this, okay, if I just show you yeah, so normal distribution, if you see here clearly, now I think you can understand normal distribution, and it's a probability density function, fine, which you have seen. And these are the examples of probability normal distributions. Okay, and after that you are having the cumulative distributions. Okay, cumulative distributions, fine. And then yeah, you are having this particular function. As you are saying, we have seen somewhere when we are discussing, we understood we can use a mathematical function, right? You can use a mathematical function to give us a probabilities. Agree? So we understood. That's why it's called function. PDF is what? Probability density function. Fine. Distribution is normal distribution. Okay, that is probability density distribution. But what is our point? We want to find out the probability of each and every value inside the distribution. So obviously you cannot calculate for each and every value. Why? Because this is a continuous variable and there are infinite possible values are possible. So you cannot calculate probabilities for each and every value. So that's why what we used PDF functions, probability density function. And when we are saying function, it should be in this form, y equal to f of x. F of x is a function. And what is the purpose of this function? Simple. It will give you the probability. Okay, it will give you the probability of the x or random variables. Okay, for each and every random variable, what is the probability for this particular function? Fine. For normal distribution, there will be a separate function. For exponential distribution, there will be a separate function. For chi-square distribution, there will be a separate function. Okay, and the purpose and the job of these functions is to give us the probabilities. Okay, fine. So now, as you can see, this is a function. So if I just go back, fine. So this is a function. As you can see, so what is this? What is this function is having? So 1 by 2 pi is same. Okay, mainly if you see mu. Okay, is this visible? This yeah. If you see 1 by square root of 2 pi rho square exponential of minus x minus mu whole square by 2 rho square. Okay, so don't worry by seeing this formula. You're not going to derive this, fine, but understanding this is important. Okay, see what are the new things over here? Mu is the mean, standard deviation, rho square is a variance. Okay, rho standard deviation, rho square is a variance. Okay, if you just put this value and if you give x any value, it will tell you the what is the probability of that x for this distribution. That is important, guys, for this distribution. Okay, now what are the factors? Understand carefully, what are the factors that are influencing this distribution? Mu and the variance or standard deviation. If you know the standard deviation, you can calculate the variance, right? So mainly mu and the standard deviation are the two values which are affecting the normal distribution. Okay. Yeah. So that means what? That means what? This is understand this important. Mu and standard deviation are the two fundamental parameters of a normal distribution. That means if you change these values, you will have different types of distributions and all of those will be normal. Fine. So see, this is normal distribution. This will also be normal distribution. Okay. This will also be normal distribution. Understand, guys? All of these are symmetric around the mean. Okay. All of these will be symmetric around the mean. Okay. And all of these are in the shape of a bell curve. Fine. All of these will have the maximum probability at the mean. Fine. Getting? But because if you play with the mu and the rho, you can generate different types of normal distributions. Fine. That means what? As I said yesterday, okay, as I said yesterday, I'm repeating it again. See, mean is this value, mean is this value. Okay, this is a mean. Fine. Here mean is 0. That is mu. What is standard deviation? Standard deviation will tell you the spread of the distribution. From where you are getting the standard deviation, guys? From the variance. And what is variance? Variance is, how will you get the variance? If you just recollect the formula, each and every value x minus mu whole square. Okay, that means what? How much each value is differentiating from the mean. Find how much each value is separated from the mean. That value we are getting, and that if you do the square root, you are getting the standard deviation. Okay, that means indirectly standard deviation will tell you the spread of the distribution, guys. This is very, very important to understand. Okay, because you will understand a lot many things based upon this. Standard deviation will tell you the spread. That means this spread, this width, right? That will be decided on the standard deviation. If the standard deviation is high, you will have a very fat distributions because the spread is more. Fine. If the standard deviation is low, you will have a bit peak thin distributions because the spread is less. Okay, because here in the first case, there are not there are not many values that are around the mean. Okay, there is a bit separation. That means if you have, it could be like 5, just I'm taking an example, 5, 10, 15. Okay, they are not very densely located. Fine. But for the second scenario, if this is a mean, okay, there are so many values around the mean. That means you will have 5, 6, 7, 8, 9, 10. Okay, they are very closely located. Fine. So just with the help of the standard deviation, you can play with the shapes of this normal distributions. But fundamentally, you should always remember all of these are normal distributions. Okay, all of these will be in the normal can be called as normal distributions. Okay, but each of it will have its own mean, its own standard deviation, and obviously variance. Okay, so as you start playing with this, you can generate lots and lots of different normal distributions. Fine. And this function, that's why this function will give you the probability for a specific normal distribution whose value is mean and rho square. So that means if my mean is 1, okay, and my rho square is 5. Fine, my rho square is 5. So if you replace this rho square as 5 and this mean is 1 and this rho square is 5, you will get some equation. Okay, the only variable is what? X. So if you keep on changing the value of x and solve this equation, you will be getting the probabilities value for x for this, only for this type of function whose not for this type of normal distribution whose mean is 1 and standard deviation is 5. Okay, and if you have another function, for example, this function, if you take here the mean is 0, here the mean is 0, and let's say standard deviation is equal to some 2, then you need to replace this rho square equal to 2, okay, and here mean equal to 0, and you will get a different equation. You will get a different equation, and then if you start giving the values of x, and if you solve the equation, it will start generating the corresponding values of y, which is the probability. That means these values, y values, it will give you these values. Okay, these values it will give you. Fine. Are you getting, guys? So as you can have different combinations of mean and rho square, you can have lots and lots of different normal distributions. Fine. And the equation will be same, only the values will be different. That's why, as you can see here also, it is saying, see, all these are normal distributions, guys. All these are normal distribution. Green is also, blue is also, red is also normal distribution. Okay, but red is a special type of normal distribution called a standard normal distribution. We'll come to that later. But remember, all these are normal distribution. Okay, are you able to understand? See, okay, see here very clearly. The green one is also normal, blue is also normal, red is also normal. But what is the difference, guys? See here. For the green one, what is the mean? Okay, for the green one, what is the mean, guys? This one. This is the mean, the middle part, -2.
Yes.
Fine. -2. And standard deviation is 0.5. Agree? Standard deviation is 0.5. And if you see, for the let me take for this one. What is this color? Let me call it orange. Okay. For the orange part, what is the only focus on the orange part? What is the mean? This one. What is the 0 for the orange part? 0. But what is standard deviation, guys? 5. Very high. Very high. So just that's what I just now I said. As you play with the normal distributions, the shapes will be different. So just now I have mentioned, if you have the small, if the standard deviation is small, okay, very low, it will be almost, the graph will be thinner. If the standard deviation is high, the spread will increase. Okay. Similarly, exactly you can observe over here. Okay, exactly you can observe over here. See here, for this green one, the mean is 2, standard deviation is what? 0.5. Okay, put it aside. For the orange one, mean is 0. For this one, mean is 0, but the standard deviation is 5. That's why you see how much the spread is around the mean. Very large, elongated. This is the mean. The graph is elongated around the mean. Getting, guys? But for the mean equal to green one, mean equal to -2, it is okay, not that elongated. Similarly, see here. This is interesting. See here, you are having blue, red, and orange around the same mean, which you can now clearly understand. Blue, red, orange. All of this, the mean is same, 0 only. Clearly able to see? 0. It is cutting all of these 3 graphs into half. But still they are not the same normal distributions, guys. Who is playing the game? Standard deviation is playing the game, because mean is fixed now. If you change the standard deviation, the graphs are changing completely. You see, for the red one, it is 1. Okay, for the red one, as you can see, it is 1. Okay, for red one, it is 1. For what is this, guys? For blue one, it is 0.2. Okay, so as it is decreasing from 1 to 0.2, when you are decreasing, the graph is becoming thinner and thinner. Understanding? So this is 0.2. But if you increase from 1 to 5, if you go, the orange one, it is getting spread like anything. Clear? So this should be very clear, because you are fixing the mean clearly, and if you just play with the standard deviation, the graphs are changing. How you are changing, you can see. Increase the standard deviation, the spread, the graph gets spread. Decrease the standard deviation, the graphs become thinner, comes closer. Okay. And also, if you change the mean, the graph shifts. Okay. If you change the mean, the graph shifts, because if you see mean equal to -2, the graph is shifting from here to here. Here it is -2. Fine. Clear, guys? Let me know, guys, if this is clear.
Yeah, Santosh.
And also here you can also make one very interesting fundamental observation. You can say mean will shift the graph horizontally. Okay. And standard deviation shift the graph vertically. Fine. So if you play with the mean 0, if it is 0, it is over here. If it is -2, the graph shifted this side. See, the graph shifted. You can just move this graph to left. If it is +2, for example, if it is +2, the graph will come here. If it is +5, the graph will come here. If it is -5, the graph will come here. Fine. So if you play with the mean, there will be a horizontal shift. There will be a horizontal shift. Agree? But if you play with the, if you play with the standard deviation, the vertical will be changing. If it is 0.2, okay, for blue it is 0.2, okay, the vertical part. If it is 0.5, this much heights. If it is 0.1, 0.5. Getting? For example, if I take very much 0.001, it will be very thin part. Okay. If I take, instead of 5, if I take some, let's say 20, it will be extremely like these guys. Getting? The heights, the vertical part will be changing. Fine. So you can also remember this way. If you change the mu, the actual location, I mean the horizontally, the wherever the mean, the horizontal displacement will occur. If you play with the standard deviation, the vertical, the height will keep on changing. Right? So in your mind, you can visualize different combinations of these. Okay. So but again, I'm saying bottom line is all of these are normal. As long as these are symmetric around the mean, without any skewness, this is a normal. But inside normal, there are lots and lots of different types of combinations can be possible. just with only two values. You don't need anything more, mu and standard deviation. That's it. Okay. Now coming back to our concept, that's why in the function you are able to see only two things you need to put here. Okay, you because he don't know the function when you are generating, he doesn't know like what type of normal distribution you are using and what is the standard deviation, the mean for that. So that's why you need to replace this. Okay, so for example, if you are in this case, yeah, if you take this case, yeah, so here let me take this green one. Okay, the green is what? -2 and 0.5. Okay, so that's why if you come here, if you take -2 and 0.5, okay, so you need to replace this. Okay, it will become 1 by square root of 2 pi. Okay, and rho square is what? Rho square is variance. And is that variance on the website? Yeah, variance is 0.5. Fine. So now into 0.5. Okay, e to the power of minus x is x value. Okay, yeah, input minus what is mu? Mu is -2, minus of -2. Okay, by 2 into again rho square is 0.5. 2 into 0.5. Okay, whole square. Okay, this equation, all these are just multiplications. 2 pi is 0.14 into 0.5. You can multiply all these or multiply. You will get the equation. The only unknown value is what? X. Okay, so this function will is doing what? For this distribution, for this normal distribution, okay, whose mean is -2 and what? Standard deviation is 0.5. Understand this, guys. I don't know the distribution. To draw a distribution, what I should have, guys? I should have the values of y also. Okay, to plot these points, I should have the values of y also. Agree? So what is this y? Y is probability. Y are the probability. Fine. The xy. So this function will help us to get this y value, to get this probabilities. That means for this function, okay, for this normal distribution whose mean is -2 and standard deviation is 0.5. Oh, this is the equation. If you can take different values of x and solve this, it will give different values of y. Okay. For example, just like if you take -0.6. Okay, if you replace this x equal to -0.6 and solve this equation, you will get some value. Put -0.4, you will get some value. Put -0.8, you will get some value. Okay, put some value. 0, you put some value. Okay, like that. If you put all these values and if you connect that, you will get a normal distribution. Fine, you will get a normal distribution and whose mean is -2 and standard deviation is 0.5. Fine. And how you are going to get this graph? You need the probabilities, and from where you are going to get the probabilities? You will get the probabilities from this function. That is the importance of this function, guys. Getting? That's why it's called probability density function. That means it will give you the probability of each and every value for this normal distribution. Okay, and this, as you can clearly see, if you change this value, that means what? If you take another value whose if it is 0 and 0.2, if you take the blue color 0 and 0.2, fine, then the equation will clearly change. Okay, in the place of here you will have 0.2, fine, in 0.5 you will have 0.2, and in the place of mu, in the place of -2, you will have 0. Fine, now this becomes completely new equation and you will have completely new values of y, and that will be different normal distribution. It will also normal distribution, but different normal distribution. And you can see you are decreasing the value of mean, so it will have a bit peak distribution, or you're decreasing the value of standard deviation. Fine. So then its y values will be different. If you solve each and every value of this equation for different values of x, you will get y values, probabilities. You can plot this. That's how you can generate different values. Okay. You can generate different values from this probability density function. Fine. So that's how, because it's not a simple example, just like you are rolling a dice, you will have 0.5, 0.5, or you are rolling or some 1/6 something. Okay, this is now the actual real scenario. In real scenario, you do any normal distribution, any event. Fine. So if you see the practical application, any event, guys, that means what? If you see a heights of person, okay, heights of person will follow a normal distribution. How do I say that? What is normal? If you take age, okay, if you take age, okay, from 0 to 5, okay, 10, okay, 20, okay, 30 and 40 or 50. So if you draw a graph, okay, so in, okay, that means what? The height is, let's say, 4, 4.5, okay, and 5, okay, maximum I'm saying 6, fine. Just a simple example for you to understand. Now, if I just draw, initially in kids will be having of low height, okay, just starting from 4, okay, as you move to 5 to 10, the height will be increasing. Let's say at the peak value, okay, around 10 to 20 or 25, the value will be high. Okay, and after that you can find the middle-aged people are having low height, okay, and old-aged people again they will bend, okay, they'll be having smaller height, fine. So if you see, the peak value can be observed at some mean average, okay. If you take the average value of the height, so from 0 to 50 age, okay, if the 25 is the average, the maximum value can be observed at the average. Okay, the maximum frequency can be observed at the average. After that, the old age are having like lesser height and the kids are also having lesser height. Fine. So this became a, we'll see other examples also, don't worry. But this became a normal distribution. The moment it became normal distribution, you will have the access to use this function freely. You just need to know what is the mean and standard deviation, because even this height scenario also, for India, there will be a mean, average and some standard deviation. For US, there might be another mean height, because in India, the average height might be, for men, if you take 5.5 or 5.4 something, but US, it could be 5.8 because they are a bit taller. Fine. And standard deviation will change. Okay. And this, and for China, it might be bit different. Fine. All these are different normal distributions across different countries. Fine. So, but all of this, if you can use this formula by replacing their corresponding values, and you will have corresponding probabilities, and you can draw a graph. Fine. That's how, when you have, that's the reason when you have some practically available scenario where you feel that it is following the trend of normal distribution, you can come directly use this formula. That is the importance of this formula. You don't need to sit and do the individual probabilities. Just replace the value of mean, replace the value of standard deviation, and put the value of x, whatever the value you want to find out the x, and you will get the output probability. This x could be anything. If you want to calculate your probability of your weight, sorry, your height, and or your friend's height, anything you can give, provided that you know the rho square and mean. Fine. That is how you can calculate the probabilities, guys. Okay, but interestingly, you don't need to do this manually. You already have the defined functions. Okay, that's anyhow the beauty of Python. But understanding behind the scenes, as I said, is always important. Fine. So is this clear, guys? Is this clear? What is the normal distribution? How the mean and rho square are affecting the shapes? Fine. And as you can clearly see, it's from this diagram. Fine. And also, what is the importance of this formula? Fine. Let me know, guys. Let me know. Is this clear? Any doubts? Are you able to understand the things honestly?
Yes,
Yeah.
sir.
Yes.
Okay, great. Happy to hear that actually. So, yeah, similarly, this is a PDF, guys. Okay, don't worry about these formulas. Okay, just understand the concepts. Okay, CDF, for every PDF, you'll have a CDF. So our normal distribution is also PDF. So this is a function and its corresponding CDF. CDF will give you what all the cumulative distributions. Okay, and to find out the quantile, mean, median, mode, variance. Okay, or skewness, or what all we have seen. Okay, we'll again come here. As you can see, skewness, it's having 0 skewness. Okay, you remember skewness? We have okay, we have discussed. Okay, this one or this one, left skewed, right skewed. Okay, but if in normal distribution there are no skewness, it is symmetric around the mean. That's why skewness is 0. Okay, so fine. These are the different examples, guys. Now with this understanding, okay, okay, this is a cumulative probability function. Okay, this is a cumulative probability function. Fine. So don't get scared about this. Okay, so it's a formula. Fine. So when we integrate the PDF, you'll get the cumulative distribution. Fine. So now we'll see one example. Okay, we'll see one example so that you will have a practical example. You will have some understanding. Okay. So for calculating this, right? So we'll use something called as normal distribution calculator. Okay, for the practical examples. Fine. Instead of putting the value and solving this, sorry, we already have some online calculator. We'll see. But the question is interesting. See, try to understand this. There is a light bulb company that has found that an average light bulb lasts for 900 hours. Okay, the average light bulb is 900 hours. Okay, with a standard deviation of 80. Okay, with a standard deviation of 80, assuming that bulb life is normal distributed, what is the probability that a randomly selected bulb will burn out in 1000 hours or less? Okay, let's try to understand this question. See, before that, when I say standard deviation of 80, okay, That's important point actually. You guys need to understand. Okay. See, whenever someone says you, whenever someone says you standard deviation equal to 1, fine. Whenever someone, for example, any standard deviation, when they're saying, it actually means in statistics, it is equal to plus or minus 1, guys. Okay. It is actually equal to plus or minus 1. Fine. That means if I say, okay, to this, the mean is, okay, the mean of this equation is, sorry, the mean of this distribution is 0 and standard deviation equal to 2. That means standard deviation will be plus or minus 2. That means 2. Okay, if let's say it is 2, it is minus 2. Okay, so minus 2 to 2. Okay, you should consider standard deviation is, it will be to the plus side or also it will be to the left side. Okay, why guys? Any idea? Because if you see the standard deviation, what is standard deviation? Standard deviation is just the square root of variance. Guys, this is important. Okay, just focus here. See, you are having, what is standard deviation? Standard deviation is square root of variance. Agree? Variance is what? Rho square. Okay. Now standard deviation is square root of this. That is just rho. Clear? Now square root will be plus or minus, right, guys? What is 4? What is square root of 4?
Plus or minus 2.
Plus or minus 2. I hope you guys know this, right? Because if you do plus 2 square also 4, minus 2 square also 4. Getting? Square root of 5. Sorry, square root of 25. Plus or minus 5. Similarly, when you are doing square root of variance, okay, it is plus or minus rho. Getting? It is plus or minus rho, because plus rho square is also rho square, minus rho square is also rho square. Sorry, square root of plus rho square is also rho. Square root of minus rho square is also rho. Getting? So that's why standard deviation, just one second. So that's why standard deviation will be, because it is a square root, it will be plus or minus rho. Okay. Is this clear, guys? Is this point clear? This is very important point actually.
Yes, Santosh.
Fine. So that's why when someone says to standard deviation equal to 2, you should assume, they will not say specifically, but it automatically means you should consider plus or minus 2. Okay. That means it could be plus 2. If it is, this is 2, it could be minus 2. Okay, you should consider from minus 2 to 2. Okay, this is one standard deviation. They'll call it as one standard deviation, guys. Okay, to tell you actual scenario, when someone says, so hey, show me the area of one standard deviation. Okay, see, now we are speaking something practical. Try to understand this. This distribution, if it is having mean equal to 0, observe carefully, and standard deviation equal to 5. Okay. Understand this distribution, I'm assuming mean equal to 0 and standard deviation equal to 5. Okay. Now when someone asks you, hey, show me the area for one standard deviation, they'll ask one standard deviation. That means for what? 1 into 5. That means what? Plus or minus 5. Okay. That means what? You need to take 5, but with a plus or minus sign, standard deviation. That means what? If for example, if this is 5, if this is minus 5, okay, so from here to here, okay, this area will be one standard deviation region. That means plus or minus 5. Okay, so if they ask you two standard deviation, it will be what? 2 standard deviation is 10. 2 into 5, 10. That this will become plus or minus 10. Okay, that means what? If you take this as 10, this as minus 10. Okay, so if they ask you, hey, tell me 2 standard deviation, that means from here to here, everything under this graph will be the region for the 2 standard deviations. Is that clear? This is extremely important point, because on this point only, the whole standard normal distribution, which we have seen here, right, in this scenario, if you observe, not this here, if you see, you are having this red color, right? Red color line. Okay, the red color line is what? If you see here, they have mentioned The red line is a standard normal distribution. Okay, this is extremely important normal distribution. It's a special case of normal distribution which we'll study. Okay, but for that you need to understand this concept. Okay, that means what? When someone says to normal distribution, sorry, standard deviation, it is plus or minus. Okay, so if I ask you 3 standard distribution, what it will be? Plus or minus 15. Okay, if this is 15, this is 15, the whole area. Clear, guys?
Yeah, Santosh.
Okay, so now if I come over here, okay, if I come over here and if I show you this example, okay, so do you have 5 minutes time, guys? Meghna, Sirisha, are you going to college? Okay,
So we are going to college.
so you have time or no to see the example?
So 5 minutes. So
Okay, fine. I'll just show you this example because we have just studied theory, right? So it will be interesting for you to understand the practical application. Okay, I'll just cover this example so that we will see some examples tomorrow. Okay, see, now just try to understand. He's saying a light bulb as manufactured a light bulb company manufacturing bulbs, and usually he's generating bulbs. Okay, and there will be some life for the bulbs. He's saying the average time for the light bulb, okay, it will burn for 900 hours. Okay, but with a standard deviation of 80 hours. This is important. He's saying average is what? See, you need to convert, always you need to convert the given sentence into mathematical formulas. So they will not give mathematical formulas, they'll just give you the practical scenario. Okay, here average is what? He will use normal word average, but what does it mean? It's called mean. So the mean indirectly is saying mean equal to 900. Okay, with a standard deviation of 80. Okay, that means rho equal to 80. Now what does this mean? You know, this means that, see, why is giving standard deviation? He's saying average is 900, but he cannot be 100% sure, right? He's generating a bulb. He has checked 900. So he has checked some lots and lots of bulbs, the average time, how much they're burning. Okay, it's not that every bulb will burn for 900. Some will be greater than 900 or some will be less than 900, but average is 900. Okay, so that's why he's saying average is 900 with a standard deviation of 80 means it will be 900 plus or minus 80, guys. That is the actual scenario. Okay, so the range is, what is 900 plus 80? 980. Okay, fine. And what is the 900 minus 80?
Yeah, 820.
820. Okay, so the minimum could be 820, the maximum could be 980, but the mean is 900, the average is 900. Okay, so that's how we need to present it. So we will say it is 900, but with a standard deviation of 80. That means 80 hours it could be more, 80 hours it could be less. Okay, కొంచెం అటు ఇటు ఉండొచ్చు అని అంటారు కదా, same thing, same like this. Okay, 900, he cannot, because how some bulbs due to the manufacturing they might burn a bit more, some bulbs due to some manufacturing defect they can burn a bit less. Fine, he cannot give guarantee. That's why he will take this error, this benefit of doubt. Fine, so that's why it is plus or minus, always it is plus or minus the standard deviation. Okay, just now we have seen, right? So 900 plus or minus 80. Fine, so that's why he's asking that is a question, guys. Assuming that the bulb life is normally distributed. See this, assuming that the bulb life is normally distributed. That means what? At the mean, okay, at the mean, it will have the maximum number of hours. Okay, that means if you see the curve, okay, it like this. That means most of the bulbs, okay, most of the bulbs will burn for 900. Okay, very less number of bulbs will burn for the less than 900. Okay, now what is the probability that the randomly selected bulb will burn out in 1000 hours? Now he's asking average is 900, that's fine, standard deviation is 80. Okay, but I want to know the probability that a randomly selected bulb, randomly I will take one bulb, what is the probability that it will burn out in 100 hours or less? See, guys, this is a curve, normal distribution. He's saying this is normal distribution. Okay, and the mean is 900. Okay, this is 900. Okay, standard deviation, okay, somewhere you will have 980. Okay, somewhere you will have 820. Okay, these are the hours. Fine. So now he's saying what? He's saying it is normal distributed. That means what? It will have peak at the mean. it will have peak at the mean. That means maximum 900, the bulbs which will burn for 900 will be the maximum. Getting the probability for this 900 will, the mean means 900, that will be maximum. Okay, but the bulbs which will burn less than 900, that means from 820 to 900 will be less probability. That means there will be few bulbs, okay, which will burn less than 900, and also there will be few bulbs which will burn greater than 900. Getting? So that's why this will become a normal distribution. But at the mean which is 900, you will find the maximum amount of bulbs which will burn. Clear? Now he's asking, this is fine. Is this clear, guys? How did the problem become normal distribution? Did you get that?
Yes.
Okay, fine. So 900 is the maximum. Fine. So now he's asking, what is the probability that a randomly selected bulb will burn out in 1000 hours or less? Okay, I want to find out, randomly I will take what is it, how much it will burn for 1000 or less. That means what x is less than or equal to 1000. Okay, when you see this less than or equal to, did something come to your mind, guys?
Cumulative.
Correct. Come on, Shirisha. This is C, D, F. Fine. He's not asking for a specific value. He's not saying x equal to 1000. He's saying less than or equal to. So x is less than or equal to 1000. So in statistical words, the complete area, I don't know where is 1000. Okay, let me say it is 1000. So all the area less than or equal to 1000. Okay. Now what is the probability that the light will burn out in 1000 hours or less? Okay. So that for that you need to use the cumulative frequency. Okay, to use the cumulative frequency, actually you don't need to use this formula. So something you directly have, if you just go and say normal distribution calculator, okay, you will find this. Okay, yeah, so you can take some normal distribution calculator. I'll just show you how you can use this. Yeah, over here you will have this value. Okay, so here, right, so here you need to give okay, what the value you need to what happened? Just give me a second. Fine, our distribution calculator. Okay, so here, what is our mean? Mean is 900. Agree? And standard deviation is 80. Okay, and what do you want? You want less than or equal to 1000. Okay, the random variable, sorry, the cumulative, so the one you want is a probability, right? The one, the raw score, that will be 1000. Okay, fine. You got 0.894. The same thing how you are getting here. Okay, here this is a normal distribution. You will have lots and lots of normal distributions. Okay, stat trick, you can use this, normally use this. Okay, so here if you give a mean value for a normal distribution, and if you give the standard deviation for that given distribution, and if you want the, for which particular value you want to calculate the CDF. Okay, when you're saying x, when you give 1000, it will take 1000 here. You can see. So it is telling you this is a probability. Okay, this is a probability for the bulb to burn out in less than or equal to 1000 hours. Okay, so that you will get from the cumulative distribution function. Fine. So apart from this, okay, so it is saying putting the values, you get a, hey, what's happening? Somebody drawing on my, who is drawing, man? Okay, so that is the probability that you will, that the bulb will burn out in 1000 hours. Okay, so Fine, guys. So that's a scenario. We'll see a few more examples tomorrow. Okay, so that we'll have a better understanding. Okay. So is the example clear, guys?
Yes, sir. Clear.
Okay, fine. Okay, so I would say we have started a very important concept, normal distribution. Just go through the class or see some examples. Okay, but make sure standard distribution is very clear. Okay, so fine. So tomorrow we'll study the extension of this. Okay, which is also called as something called as empirical formula, which is the basis of the normal distribution. And then we are going to study. Yeah, so then we are going to study something called as standard normal distribution. Fine. We'll also see some examples. Fine, guys. Tomorrow, are you guys joining tomorrow? Let's have a class tomorrow.
Yes, sir.
Okay, fine then. So let's meet tomorrow. Okay, Saturday, same time, same link. Fine. Thanks. Thanks, guys. Thanks for joining. Chalo, bye.